has years of experience doing this in various locations around the country, and because of this this work, we did this here in Fresno. And I'll put my cursor. So anyway, particles come in through a tube right there. They are dried. They go through various stages. The particles end up coming down through behind this curvy tube. They're coming down in here. This is purple guy is a laser that throws a lot of energy into the particles, ablating and ionizing them, making a plasma, and then the ions are accelerated down this time of flight tube, and we get a chemical composition of each of the particles one by one. It's an instrument that I invented about 15 years ago. Okay. Now, so let's look now again at the summer and the winter and what the general categories are of particles that appear there. And the cursor was just there, now disappeared on me. There it is. Okay, so here you're seeing a pie chart, which is for the size of particles that we were looking at, which is around 100 nanometers or so. What is the different prevalence of chemical composition of these particles? So we have different classes of particles, and this is for the summertime. What you see here, so the most common class are elemental carbon particles that might be emitted from, say, diesel or other kinds of combustion processes. And those are particles that have very little organic carbon. You've heard about elemental carbon and organic carbon. This thing just doesn't want to stick with me, does it, this cursor? You heard about elemental and organic carbon. So the organic carbon is the more clear, oily stuff. The elemental carbon is the more black junk that you might see coming out of an older diesel truck. The newer ones are much cleaner. So anyway, you see that along the side there's the EC, which stands for elemental carbon. There's the potassium, which is a metal that's indicative of biomass burning and other sources like that. AN stands for ammonium nitrate, one of these compounds that's formed in the atmosphere that then condenses on particles, and et cetera, et cetera. So you see the prevalence of particles there. Now, what you see, one of the take-home messages here, of course, is there's a wide variety of particles, and because we are looking at the particle composition one by one, we actually can see the heterogeneity in the different particles and sources that are affecting Fresno during different times of the day and different times of the year. But one thing you do see here is very little in the way of secondary compounds. You do see a little bit of ammonium nitrate, and OC is there too, some of which is secondary. We talked about secondary and primary sources yesterday. If we go to the winter, though, you see a lot more, you see a very much big change in the distribution of these particles. You see a lot more potassium. That's indicative of much more biomass burning here in Fresno, because people use it for heating and other sources, other reasons for biomass burning. And then you see mixtures of, say, that's the first class is the potassium, the second class, the potassium, ECOC, ammonium nitrate. A lot more ammonium nitrate, a lot more organic carbon spread out on the particles, because a lot of that is this secondary material that, when formed in the atmosphere, condenses on the stuff that is emitted by the primary sources. So again, another view of what's going on here in Fresno. So now let's ratchet it up yet one more time. Here's a kind of a paradigm for what happens in any location and how we deal with regulation conceptually related to air pollution. And this is going to segue into another instrument that we've been using. So basically, you've got two sources of particles and their precursors in the atmosphere. You've got natural and anthropogenic. If you look on the left side of the screen, there's atmospheric processing of that material. And then that causes various problems that we care about, like health effects, climate change, and so on. Then regulators, find out that there's a problem and institute regulations that then control at least the anthropogenic emissions, and hopefully we don't cut down all the trees and things and get rid of the natural emissions too. So what we're interested in is how to do better regulation. Now, one question are all the particles in the atmosphere created equal, or are some more equal than others, as George Orwell would say? That is, are some more toxic? So right now, we control all particles in the atmosphere the same, basically based on their mass. But we don't expect that, say, sea spray particles and diesel exhaust particles would have the same toxicity. People voluntarily go to the beach and breathe diesel particles. People don't generally go hanging around the bus depot wanting to breathe diesel exhaust particles, and there's a logic there. Okay? So the question is, can we get more at the relative toxicity of the different particles in the atmosphere by doing some clever sampling? and because of my lack of time, I'm going to skip these. So what's the big idea? The big idea is to take that single particle analyzer and to use that to tell us how to sample particles out of the atmosphere in a way that we can then deliver the particles from different sources or source combinations to toxicologists who can then do relative toxicity studies on them. So here's the concept. Here is, if I can get my cursor, yes. So this is the single particle instrument. We have 10 high volume samplers that collect size segregated particles. So we bring the particles in, we get rid of some of the larger particles, we sample some of the smaller particles, and we control which one of these is operating by seeing what the single particle mass spectrometer is receiving in real time. So it's actually out there in the field getting the particles and sampling them onto one of these samplers. And each of these samplers we have assigned to a different composition, so that we're only collecting on that, or we're trying to only collect on that sampler just what's different compositions, so we can then do the relative toxicity analysis later. Here's what it looks like in Fresno on Shaw Avenue. And here are some compositions. So here, for instance, is one of the assignments where we have, as you saw, the potassium particles, which are indicative of biomass burning, are a huge factor, and the other factors are not. So that's a very simple sort of source combination of junk you might see here in Fresno. And here is one that's a little more complicated. Also, the biomass burning is there, but also you see biomass burning particles with ammonium nitrate secondary material condensed on top. You see them with elemental carbon and other secondary material, et cetera, et cetera. And these things come together and we sample them separately. And then here, finally, are some time distributions of these different source combinations that we've seen. And you can see some of them occur more in the morning, some of them occur more during the daytime, some of them occur more during the evening. Each dot there represents a 5-minute time period which is dominated by a particular source or source combination at Shaw Avenue. Basically what we saw in those pie charts earlier. And that's what I have to show so far, and we're still working on this, and you'll hear more later this morning from toxicologists that we work with who will soon be taking some of the source-oriented material that we sampled here on Shaw Avenue and looking at the differences in toxicity to then inform regulation about which way we should be, which sources are more toxic than others, which should be regulated more. So anyway, thank you for hanging with me, and for my supporters, the California Resources Board and the Electric Power Research Institute for supporting this work.
Thank you very much.